So hello everyone, this is lecture 16 for electricity and magnetism. In the last lecture we were discussing the image problem. So let's move forward. There is this question. A uniform line charge is placed on an infinite straight wire, a distance d above a grounded conducting plane. So you have some conducting plane, okay, it is lying in the xy plane, and there is this infinite long wire which is in the x direction, and this line charge is placed at this distance d distance from this plane sheet, and this charge density lambda. So now what we need to find? We need to find potential in the region above the plane. So above the plane means somewhere here we need to find the potential. Find the charge density sigma induced on the conducting plane. So what is the charge density induced on this plane due to this charge? So we need to find that also. So how can we find? First we need to make a equivalent form of this structure to find the things. Okay, so we'll use the image concept. So here is this plus lambda, so we'll assume minus lambda in the negative of this plane, that is minus lambda. Now why we take this? So now if you take the potential at the origin due to these two charges or line charges, this will give you total potential 0 here. So this is the equivalent form of this. So now we need to find the potential at this p point, which is in the yz plane. So x will be 0 and yz. This distance is r plus, this distance is r minus. So simply we will use a formula for the potential due to infinite long wire. So we know for infinite long wire what will be the potential. Means we know the formula, we already derived this, that is minus lambda by 2 pi epsilon log r by a, where this r is the distance from the wire of that point, and a is some arbitrary constant from where we are, means this is a reference point. Like you have a straight wire and you have to find the potential at this point, which is r distance apart. So the amount of work done required to bring any unit charge from infinite to, means from any a point to this r point, so that a is something reference point. So that is your potential at this point. So for the r plus, we'll write r plus here. For r minus, the distance is r minus, so we'll write r minus here. So total potential is nothing but sum of these individual line charges. So we will be v plus lambda and v minus lambda. So v plus lambda will be minus lambda, means because of this minus charge, minus sign. So minus lambda 2 pi epsilon log r plus by a, and for this minus lambda it will be lambda by 2 pi epsilon log r minus divided by a. So this is a simple formula we know. Now how to find this r plus and r minus? So r plus is simply this distance is given by, take this a right triangle, so this complete distance is nothing but z, so z minus d, sorry, this will be your this distance. So this r minus can be written as, so this r plus square will be equal to, this will be z minus d square plus y square, and this will be equal to r plus square, and for the r minus square this will be equal to this z plus d square, and this is y square. So you will just substitute the values for the r minus and r plus. You will get v equal to lambda by 4 pi epsilon naught. This a will be neglected because this will cancel out when you take the log. It will be log this divided by this, so r minus square r plus square. So this will be your potential. Now you have the potential in the yz plane above this plane. So if you have the potential, you can find the charge density. So for the charge density, we know the formula minus epsilon d del v by del n, or del z, for z equal to 0. So this will be your charge density formula, and you know already the potential. So just take the differentiation and put the z equal to 0. This will be your charge density, and this is the function of y. See, this is in the y. Okay, so that's how we find. Let's see the next question. A point charge q of mass m is released from the rest at a distance d from an infinite grounded conducting plane. So you have a grounded conducting plane, and some charge is released above some height at a distance, means it is distance d. Okay, write the speed of the particle as a function of distance. Now this particle will be attracted towards the conducting sheet, and then we need to write the speed of that particle with respect to distance from that particle to that sheet, and how long will it take for the charge to hit the plane. So that time also we need to check. So we need to just take the image problem. So in place of the sheet, we can remove this by the minus q charge. Now this distance is x. So see, the force on the charge will be, let's say, defined by m d square x by dt square. This is the formula for force, and this is your acceleration. And this force is nothing but simply q minus q divided by 4 pi epsilon 2x square. So this will be equal to this. Now from here we can find this d square x by dt square. That will be equal to m will go this side, and some constant terms will be there. So we will take that constant as a. So it will be minus a by x square, where a is q square by 16 pi epsilon m. Now see, this is nothing but acceleration. Acceleration can be written as dv by dt equal to minus a by x square. Now multiply with v to both sides. So here v is this and v is also dx by dt. Now take this v dv by dt and it can be written as d by dt of a by x, because differentiation of this will give you minus a by x square. So why we are doing this? We are doing this to find the relation between the speed and the distance. Okay. So let's do this. Now this will be d by dt of v square by 2 and d by dt of this. So this can be equal to this and plus some constant. So now we have the relation v and x, but we need to find its constant also. So see, at x equal to d, means when the particle was at d distance, the initial velocity was 0. So at x equal to d, this will be 0. So c will be minus a by d. So substitute here, you will get the relation between v and x. So this is your formula. This is the a part, that what will the how the speed will change with distance. Now the question can be asked something like this, that if when x equal to d by 2, speed is given as u. So you need to find what will the distance of the particle when the speed is 2u. So you just find the value of a first by putting x equal to d by 2 here and here u. So substitute the a again and then find the x. So you can solve this, you will get x equal to d by 5. Try to solve this. Then there's this b part, how long will it take for the charge to hit the plane? So that time we need to find. So we know speed is nothing but minus dx by dt. Why we have taken this minus dx by dt? Because x is decreasing as charge is approaching the plate or the plane. The dx is decreasing, so the speed must be positive. So that's why we have taken this minus sign outside. Now this is equal to root 2a d minus x by xt. We already find this relation v and this. So this is your v. Now how we integrate? Just to use the separation of variable method. Take this x terms with the dx and dt here. So let's take the t time to hit the plate, and 0 to t, and x will be going from d distance to 0. D will become 0, mean distance from the charge from the plate will become 0, so d to 0. So x is this and t is this. So now to solve this integral, just put x equal to d sine square theta, then you will be able to solve this, and the integration will give you this result, minus d 3 by 2 pi by 2, and this will equal to t minus root 2at. Now you have the time equal to pi d 3 by 2 under root 2a. So this will be your time for the d to become 0. So it means the time required to hit the plane, and you know already the value of a. We write this here, substitute it here, you will get the time. So this will be your time, means to hit the plate or the plane. Let's see one more question. A point charge q is situated a distance a from the center of a grounded conducting sphere of radius r. So this is your conducting sphere of radius capital R, and this charge is placed here at a distance a from the center of the sphere. And what we need to do is find the potential outside the sphere. So if there is any point P which is making theta angle at the r distance apart, small r, so we need to find the potential at this P point. Find the force experienced by the charge q. What is the force experienced by this charge q due to this conducting sphere? Find the work done in placing q at a distance a from the center, and what will the work done required to place this charge here at the distance a. So first, to find the potential outside the sphere, first we need to make a image problem, means equivalence of this. So I won't go into the derivation. I've just told you that I will tell you that how to simplify this. Just whenever you get this kind of situation, the equivalence or the image problem will be, assume some q dash charge due to this here, means it can be here also, here also. Let's say it is q dash here, and if this is your origin and this is a distance, then that q dash will be b distance. Okay, now this is again from the q dash, this will be r1 dash distance, and from the q it is r1, the p point, and from the origin it is again r, and this is theta angle. So what you need to remember is that q dash will be minus r by aq always. This r is the radius of the sphere, and this a is the distance from the origin to that charge. So this q dash will be this, and the distance of this q dash charge from the origin will be r square by a. So a and q and r are known. So now we have find the q dash and b in terms of the known terms. So these are your all known terms now. So you must remember these results, very important. Now we can find the potential very easily at this point, because potential will be simply sum of the potential due to q dash and q. Because of q dash it will be q dash by 4 pi epsilon naught r1 dash, and due to this it will be q by 4 pi epsilon naught r1. So this, and now we know already the value of, now you need to substitute the values here in terms of the known terms. So what will the r1? So r1 is nothing but this is r, then this will be r sine theta, and this is r cos theta. So r1 will be r1 sin theta square, and this is your a distance, so a minus r cos theta will give you this distance, so square of these will give you r1 square. And same for the r1 dash, this it will be r cos theta minus b square plus r sin theta square. So that's how you can find r1 dash, and you already know q dash equal to minus r by aq. So substitute all the values here and you will get your potential in terms of r and theta. Means now you have the potential in all the non terms. So see how can we verify this potential. So we know the equivalence should be like that, potential at this sphere must be 0. So if put small r equal to r, then potential should be 0 at this point. So let's substitute in place of r capital R. So what you will get, capital R square a square 2r a cos theta, here r square, if you place r here, so it will be a square again, r will cancel out, and r a cos theta, so these two terms will be same and they will cancel out, become 0. So means this equivalence is correct. So this is your potential at any point outside. Now if you need to find the charge density and on this sphere anywhere, so that will be equal to minus epsilon del v by del r, and r equal to r. So that's how you can find the charge density also. Now find the force experienced by the charge q. So if you need to find the force, so this will be simply, this is equivalent to this. So force will be q dash q divided by 4 pi epsilon naught, and this a minus b distance square, distance between q and q dash. Now substitute the q dash and b, so you will get your force. So this is your force. Now there is a third part, that is find the work done in placing q at a distance a from center O. So what is the work done required to place this charge or place this charge here? So that work done will be force multiply the displacement, and the limit of the displacement will be infinite to this distance, means a. Okay, so just substitute the limit, it will be f dot dl. So we just need to put the magnitude of the force. This will be this, so magnitude is this, and dl is dx, and in place of wherever we have a, we will place x, because a is representing the displacement from the origin. So we'll substitute the x because we are putting it from infinity to a. Now when you integrate this, you will get the negative sign, because the work done for a charge to place near the conductor, it will be negative because it is attracted towards it, so it will always be negative. So when you solve this, you will automatically get the negative sign. So this is your work done required. Okay, so that's all. Here we end the electrostatics. Okay, in the next we will start the next chapter, that is motion of charged particles in the electric and the magnetic fields. So that will be your next chapter. So thank you everyone.